We had bad examples, bad experience.
Yes, sir.
Somebody made trash. No, it happened to us at Colloquium, and it was very against it. Yeah, I think we have.
No, it's fine.
Yeah, please come in. Okay, so let us get going. Good evening and welcome to. Beforehand, I can tell you probably one of the best colloquia that you would have heard in the recent times. And not just because it is given by somebody like Amit, but also about the matter that you're going to kind of see about the material that is going to be kind of useful to wide across the departments here. I think that's what GRK and Vaibu are talking about. It's important that people come down here to kind of not just only listen, where of course you could do on let us say YouTube and Zoom and so on, but the kind of interaction that one would be benefited, I think it's something very, very important. And a few days back, Jyotishman was talking about the colloquium, and one of our students come and said, "Did you attend this colloquium?" Because he's talking about, let us say solar cell, certain way of generating. You never know where the ideas come from, right? And it's quite phenomenal. Many times people talk about, oh, I got this idea sitting in West Canton table and discussing. So it's a humble appeal to, again, all of you, those who are here and also those who are probably listening on the virtual channels. Please come down to AG 66. The feeling is quite phenomenal. It's not same as sitting on your desk and doing multiple things. And you think you are attending the talk, probably you're not doing. You think you're doing work on the desk, probably you're not doing. And you're missing cake and chai, etc. in the process, right? So with that little appeal, so let me start. Of course, today we're going to hear from Amit something catching extremely fast. Obviously, this fast is, they don't talk anything less, more than picoseconds and very, very high density, 10 power 18 watts per centimeter. And I mean, these are numbers which are mind-boggling. And now how to kind of image, how to kind of scan at least the 2D image of these pictures with precisions of, let us say, picoseconds and micron kind of resolutions. I mean, that is a kind of technique and which stretches the limits of technology to do the science that we want to do these days, okay? So that's a very interesting story that he is going to kind of say today. And he kind of alerted me, don't say too much about me because people all know these people are very, very high intensity, very, very highly visible people, so they don't need any introduction. But I think it's my duty to say he did his PhD in Pune University way back in 2009. And then he's actually he leads TIFR's 150 terawatt system laser facility, has more than 80 publications in many national, international journals. He has given many talks, invited talks, both on national and international conferences. He's an Infosys TIFR fellow and also been awarded Dr. Parviz Guzar Young Scientist 2014, and also Dr. R.K. Balla Young Scientist Award in 2008. With this very, very short, because everything is short and intense, I invite Amit to start his colloquium.
So thank you, Satya, for such a nice introduction, and welcome all of you. Good to see people in person, and some of them are also joining from a Zoom, so welcome all of them. So today I will be taking you to my lab, giving several glimpses of catching the plasma on its ultra-fast time evolution. So when we say about ultra-fast here, I basically mean femtosecond and picosecond time resolution. And I will take you to the lab where we will show how such processes happens. And I will tell you in situ they are operating, as well as the location where it actually happens. The main heart of all this problem which we are trying to solve is the major workhorse of our all experiment is TIFR 150 terawatt laser. This laser got installed in 2013 to the power of 100 terawatt. I've talked in my last two asset colloquiums, but very recently in 2019, we have upgraded this laser from its peak power of 100 terawatt to 150 terawatt, and this is regularly operating in a lab, and we have beam time as high as 90%. So the laser is, as I told, ultra short, 27 femtosecond is a pulse width, and the wavelength of this laser is infrared, 800 nanometer plus minus 40 nanometers, whereas the beam size is huge. It's more than a 3-inch diameter of a beam. We focus as such high power pulses to a micron size focal spot, and where we can generate the intensities of the order of 10 to the 19 watt per centimeter square and higher. So what, sorry.
Red color, which is the flat top. Is it a flat top?
The beam is the flat top. This beam is a flat top. But when we focus onto the target, this is a Gaussian beam, but this is a flat top beam. So energy is distributed quite evenly across the whole area. So when we achieve such intensities, and when we these are focused onto the target, there is a generation of hot and dense plasma. There is an immediate generation of an very hot and relativistic electrons, which started flowing into the target with velocity of c/7, heating the target portion and thereby transporting the laser energy deep into the target. This plasma is a source of several another excitation, like it can emit X-rays, gamma rays, terahertz. We can have a nice relativistic electron source. It can give ions, neutrons, protons, whatever you have talked about, whatever you can think about. It can have the ultra high current density, and because of its motion, it can also generate the ultra high magnetic fields. But as we are talking, this is highly evolving plasma. So it's moving at the speed of 10 to the 6 to 10 to the 7 centimeter per second, highly emissive, hugely environment, can be extremely noisy, and we have to do the selective measurement of this plasma in such highly turbulent environment. So here I will be today talking about the motions happening in ultra fast time scales, measurements done in such turbulent and noisy environments. And as I said, this plasma is rapidly evolving and rapidly flowing. So all the parameters can change in ultra fast time scale. So these are some of the snapshots of work done in last 5 to 6 years. We have basically developed single shot high resolution 2D Doppler velocimetry to measure the precise velocity of the motion of this plasma. We have developed a spectral interferometry to measure a nanoscale preform plasma. And also we have generated efficient second harmonic pulses which can now enable us to do a very ultra clean science. So I will also talk about how these have been generated and how being used as new laser pump pulses as we progress. So exactly 10 months and 1 week ago, Ravi has beaten us red and blue by giving with the shocks, where he has talked about the generation of an plasma and thereby the motion of a shock. More main physics part being discussed by him, but today I will talk about the techniques by considering the spirit of the asset colloquium, and I will show you how these measurements are done on day-to-day basis in the lab. What are the observables and what are recently TIFR a field is interested in. So these are the three topics mostly I will be conveying on ultra-fast dynamics, time scale, and I will talk about what are the basic challenges we face in day-to-day operation and what are the major challenges we face while we do such measurements. So as we are talking about the techniques, what we basically do in the lab is something known as a pump probe technique. So we are doing it for several years now. We have a intense light pulse, which creates hot and dense plasma, whereas this weak light, which is time delayed, actually interrogate this plasma at later instant, and we can get a full information of the plasma evolution. So this is, as I showed you, this pump creates extremely high density plasma here, and it started flowing as a function of time, whereas we probe this plasma using a second harmonic probe pulses. We can in principle use even higher harmonics. They actually non-perturbative. They touches this plasma, gets reflected from the plasma, it basically hugs the surface, and we can use as I told you, we can use the higher and higher harmonics of the plasma. They are being delayed as per our wish, and their properties are controllable. Also, once they reflect from this plasma, they can be fed to different devices like photodiode CCD, polarimetry, spectrometry, depending upon what kind of measurements actually we are looking for. That the basic question is, where does this probe reflect from? Actually, when we create a very hot dense plasma, it started flowing very rapidly towards the vacuum. And if you have incident probe, it can go deeper into the plasma till the plasma frequency matches with the frequency of the laser and gets reflected from that point. So this is where we call it as a critical layer or critical surface. So it gets reflected from this critical surface. Suppose I have a pump, which is a probe, which is close to the pump, it will get reflected from this surface. But as I'm having a second harmonic as a probe, it goes much deeper into the plasma, as much as 4 times of this critical density for the 800 nanometers. So we can really go deeper into the plasma. We can access the real high density of the target of this plasma, and we can thereby do the several measurements. So as we are talking, there is several advantages of this pump probe technique. These, as I told you, these properties are completely controllable, but what you get is what you give. Because of the probe, we can do these measurements quite far from the target. There are 2 advantages of doing that. First, there is nothing which is in the contact of to the plasma. No probes, no physical probes, but light as a probe. And as we are talking, that noise can be an essential role, but as we are moving far from the plasma, noise actually falls by 1 by r square. And what essentially we get is the real nice signature of the reflection of a probe from the plasma. So this is the laser room, as I showed you, B136, where this is a pulse compressor, which is actually at the end, they are giving ultra short pulses. These pulses are getting transferred to the another room in B136, where our experimental chamber is sitting. The whole of this path is around 10 meters, whereas even inside this compressor chamber, beam travels more than 8 to 10 meters. So 20 meters of the total travel. And in day-to-day operation, we have to always worry about very small vibrations which are taking place. Because of this, we also have to take care of the beam drifts. So small vibration can give us a beam drift. Temperature changes in a lab can give us a beam drift. So we have installed several cameras in our laser system where we can monitor the beam position, beam energies, as well as the minor drifts. Also, our pulse compressor chamber has the final mirror, which is completely controllable inside the vacuum. So small drifts also can be corrected at experimental site. As 1 milliradian drift can cause a 2 centimeter drift. That's what we have calculated. So very minor corrections has to be do every time when we start the laser. It needs actually real time to settle down even the small beam drifts, but we can always correct them as and when there occurs. Several irises has been installed throughout the laser beam to monitor and control this beam drift. So every time we correct the beam drifts, because what we are dealing with is a pump probe. So this is the experimental chamber where the scene of action is actually happening. Probe pulses, pump pulses are being taken to this chamber, to this beam line. The diameter of this chamber is as large as 1.25 meters. The target is sitting at the center, and all the measurements are carried out outside this chamber. So taking you inside the chamber, this is how the pump pulse will pass through. So basically, pump pulse will come from this end. It gets reflected by this several mirror. You can notice a beam splitter here. A small part of the beam is taken outside the chamber as a probe pulses and can be manipulated outside. This creates a hot dense plasma here, and we also need to match the probe which is coming to this location. So from the beam splitter, this pulse is coming out, which is actually getting converted into a second harmonic with the help of the second harmonic crystal. BBO here gets cleaned by the BG39 filter and again transported inside. As we need a control on the temporal part also, we move this retroreflector to and fro such a way that we can add or subtract the probe path from the interaction. So we get probe before the arrival of plasma pump and after the arrival of plasma. So this parameter is completely under our control. Once we converted them into second harmonic, sufficient delay is added. These pulses can taken inside the chamber. They get reflected from either a cold target or at a negative time delays, or from the plasma, and they get reflected back. They have been collected, collimated, and transported back outside the chamber for the measurements. So for us, every laser shot is an independent experiment. So as I'm showing you, this is a main pulse which comes to the beam splitter, gets splitted into two parts. One is acts as a pump, another acts as a probe. It's get onto the target, generates a plasma, and then probe can get reflected from there. Here, I'm showing a target which is half air coated and half glass. You can see the nice circular spot created by the pump, and the probe is basically getting reflected from such location. Yes, I will come to that, how the focusing is being achieved. So this is the whole experimental setup will look like once this retroreflector is there. As I showed you, to add the time duration, we can add as fine as 1 micron, which is 7 femtosecond, but we are limited by the pulse width of the probe, which is 80 femtosecond. So 80 femtosecond time delay can be easily added, converted into second harmonic, get reflected from here, and has been fed to PDC series depending upon the measurements which we are going to carry out. As I told you, we need a second harmonic probe. We converted using a beta barium borate crystal, which is a second harmonic crystal. This is of the dia of 20 mm and 1 mm thick, and the conversion efficiency of this is 22%. There are definite advantages of using second harmonic pulses over the fundamental, because one can completely eliminate the noise created by the 800, and one can only look at the 400 signal. Also, as I told you, that this 400 can go deeper into the plasma, so we can access the real solid density of the plasma. And if you see the fundamental spectrum, it's as broad as 52 nanometers, whereas the second harmonic is very sharp, around 2 to 3 nanometer. So very small spectral changes in case of Doppler spectrometry can be achieved with the can be seen nicely with a second harmonic probe beam. So sharp to omega profile makes it easier to see very small changes. Yes.
So why is the peak of this second harmonic not an half the maximum?
Oh, okay. It actually depends upon the way you tune this second harmonic crystal. So if you have the phase matching condition which varies slightly, you can actually tune this basically from all the way up to 390 to 410. So it's up to you, and it's up to the basically the crystal and at a particular time orientation of an crystal by which you can actually change the second harmonic creation. But efficiency almost remain the same overall. Even though there is a slight phase matching condition mismatch, but because our input to this crystal is quite high, it can be a few millijoules. So we never normally it gives 22% of an efficiency, which is enough for our measurements. So before starting the experiment, we have to match the pump and probe, not only in space, but also in time. As I told you, we can easily match them in the space with something known as a heat and burn technique. So we have a camera installed in a video zoom camera installed in our experimental chamber, which can look onto the target and help us to match this pump and probe pulses nicely. There can be small jitter in the beam because it travels too much of a path. Every shot has to be matched before acquiring the data, and you have to move the target to the new location every time. Also, we have to do the temporal time matching, and we use reflectivity to do such thing. So here is one of the example. You can see we are using the glass target for the reflectivity measurement. You will see why. The probe pulse, basically, if it comes ahead of the plasma, ahead of the pump, it's basically get reflected from the cold target. And what you can have is a cold reflectivity from the glass, which is as small as 8%. But when pump and probe comes together, it will basically get reflected from this plasma. This plasma suddenly makes the BK7 glass target as a plasma mirror. So the reflectivity of the probe goes up. So you can basically go from 8% to all the way up to 48% in the reflectivity. But as time progresses, when probe is delayed after the pump, it gets reflected from this plasma, but this plasma also start absorbing this probe, and you can see a nice decay out of this. So from this sharp increase in the peak, you can basically find out the temporal matching of pump and probe. So this is how it will look like. You can see that it's a very sharp rise, and we can find out a temporal zero at a with very high accuracy. As we were talking about this 400 nanometer probe gets reflected from its critical surface, for us, critical surface is very, very important because it plays a very, where the all basic fundamental physics things are happening, where most of the light coupling is happening at this location. Strong plasma oscillations are set at this location. One can actually upshift and see the higher harmonic generation from such a clean, nice critical surface. Giant electric and magnetic fields can also be measured at this critical surface. So this critical surface becomes a very important part of our measurement. This critical surface, as we are talking, is basically generated, but it's not very static. It's rapidly moving as a function of time. So how to probe such rapidly moving critical surface? So the answer lies in pump probe Doppler spectrometry. So the spectrum measurement becomes very important, gives a very important tool because it gives us a handle on the wavelength shift. So from the wavelength shift, either it's moving towards blue or red, you can calculate, you can determine the direction of the motion. And from the amount of shift, that is delta lambda as a function of time, you can basically calculate the velocity of this velocity of the critical surface. So coming to my first topic, I will talk about the two-dimensional velocity mapping of the plasma surface. So as we are talking, the Doppler spectroscopy for plasma, if the probe is getting reflected from this surface, it can have the blue ship. And as we are saying that plasma is rapidly expanding, we may only expect the blue ship. And this is the overall experimental schematic, where now this reflected probe has been fed to the high resolution ocean optic spectrometer, and also a small part of it has been fed to the one of the CCD to see the reflectivity changes as it happening at a target surface. As we are saying that these plasma dynamics are ultra fast, they are evolving at tens of picosecond time scale. These shifts are extremely small. So we may have to measure very, very small shift of the order of 0.1 nanometer or so. So we need a spectrometer which have much more higher resolution than that. So we are using Ocean Optics HR4000 spectrometer having 4000 pixel across the CCD, and its dynamic range is only from 350 to 445 nanometer. So we can basically see it has a basic resolution of 0.04 nanometer. So 0.1 shifts can be easily make out with such a nice, highly resolved spectrometer. So this is the first set of data. We have saying very initial time scale at 1.3 picosecond, a slight red shift, but as time progresses, we have seen a huge blue shift. This is a difference spectra. So from each spectrum, the 0 picosecond time delay is subtracted, and now you can see that from valley to peak or peak to valley subtraction difference amplitude, you can make out that it is really moving towards red, or it is really moving towards the right. From so we get up, we do this dynamics all the way up to the 25 picoseconds. So initially, as I said, there is a very small red shift followed by the huge blue shift, and we can calculate the instantaneous velocity of this, and we found that the velocity is as the order of 10 to the 10 to the 7 centimeter per second. Very initial rate, basically the plasma actually produces a shock wave kind of a disturbance, produces a compression wave, which moves the critical surface towards the target. So initially we get a red shift, but as time progresses, this compression wave basically propagates deep into the target, and we cannot access that region. And what we can see is only rarefaction wave. This probe basically sits on the rarefaction wave, and that's what we can see, the complete blue shift. So once we have seen such signature on a shock waves, we have started controlling this dynamics on the femtosecond time scale. We are starting varying the pre-plasma conditions. We have started looking towards the target rear and target back. So this has completely opened a new domain of seeing the plasma evolution. But till now, what I have shown you is that the reflection of probe is getting focused by this lens and taken to the spectrometer. So what we have seen that it's completely time resolved, but completely spatially averaged. So we are not getting a space resolved information. We are getting only a time resolved information. We are getting time resolved information where the plasma, but actually if you see the reflectivity, it's completely non-uniform. It has a two-dimensional in nature, so it may have different velocities at the center, it may have different velocities at the edge, which is not seen right now. Right now only we are seeing is a integrated effect because of the lens. So why are we interested in measuring the actual two dynamic space resolved, and one third dynamic is a time? Why we are basically interested in this motion? Because then you can completely formulate the shape of the plasma. You can map the two-dimensional velocity of the plasma. you can calculate the spatially resolved plasma scale lengths, and more insights can be given towards the shock evaluation and shock propagation. So how to measure actually the two-dimensional motion of the plasma? We need to have a space resolved as well as time resolved dynamics. So here is the answer how. What you can do is, once your probe gets reflected from the plasma, you can scan your spectrometer fiber across this probe completely, and you can get the information. Suppose I'm scanning it across, I can get the information at several locations of the probe pulses, and from that you can inform the dynamics happening here. But suppose I wish to locate at 15 points here, and I want to do the dynamics over, say, -5 to 20 picosecond with interval of 1 picosecond. So these are 25 time delays. And each time delay, for having a good statistic, we have to average it 5 points to 10 points. Suppose I consider 5-point averaging, then the total shots required is quite huge. You need close to 2,000 shots, but the target is limited. You can mostly have 200 shots on a target, and extremely time consuming, completely inefficient process. So how to deal with this? To deal with this, we come to a new innovation where instead of scanning it one by one, what we have done is we have placed a chuck here with different fibers, and all these fibers are connected together and fed to different spectrometers. So we use 16 high resolution spectrometers, which are HR4000. They are single shot. Then what we get is a multi-channel spectrograph, and this is how it looks like, and this is how the chuck looks like. Once we insert the fibers to this chuck, we have to do one-to-one mapping of this before it fades to the multi-channel spectrometer. And this the chuck with a 500 micron hole has been made here at TIFR with the help of our central workshop. Mr. Siddeshwar Chavan helped us to make it. And then you can fade it to the 16 different spectrometers. This is how you can do it. So now our high resolution multi-channel spectrometer is ready. We have this fiber array, and it's connected to all the spectrometer. All the spectrometers can be triggered with one single laser shot. So we have made a trigger box which is inbuilt. Each spectrometer has a resolution as high as 0.4 nanometer, as I showed. HR4000 has that resolution. You have 16 channels looking at 16 spectrometers looking at this area of the probe, and all the spectra can be seen together, manipulated together onto the screen. Very recently, we also have used lenslet array instead of this fiber, so that this can be focused onto this fiber very nicely to improve the signal to noise ratio and improve the intensity going on to each fiber. This is just a side view. So our spectrometer is basically now ready to do the measurement. Time dynamics is easy. You can add several time steps to have the huge high temporal resolution. And here we are only showing 16 spectrometer, but they can also be increased by increasing the number of fibers and number of number of spectrometers, and the whole transfer dynamics of the plasma can be mapped. So this is the whole experiment looks like. Probe gets reflected. In imaging mode, we have these 16 fibers which are going to the single shot spectrometer. This is basically all laid by Kamlesh Jana. And this is how the fiber chuck or my lenslet array look like. We have nomenclature them as electronic shell. So we can basically see the dynamics happening, and thereby we can conclude, we can infer how 2D dynamics are basically happening. So this is the first set of data. At very initial time scale, what you can now see, these are the 16 spectrometer giving independent redshift. You can see initially it's getting redshifted. As time progresses, you can also see the sign changes, and you started seeing the blue shift. You can see the huge blue shift at the periphery. And as time progresses more and more up to 20 picoseconds, you can completely see that plasma is flowing towards you. And from this Doppler shift, we can all, of course, measure the velocity. And what now you can get is complete information on 2D dynamics. So what we are here are looking into complete information, complete evolution, 2D velocity maps. In a very significant blue and red shift can be made out. And this is a complete plasma evaluation in time as well as in space. Coming to my second topic, till now, what I have talked about is the evaluation of this plasma. But what about the evaluation of the phase of this plasma? As this each and every femtosecond pulse can generate the hot dense plasma, but this ultra short, ultra intense pulse also has its own history. Suppose, so this is how my femtosecond pulse look like when I plot it into a linear scale. But when I plot this into the logarithmic scale, this pulse actually shows its real nature. So you can see that in the logarithmic scale, you can, if you have the intensity of the order of 10 to the 19 watt per centimeter square at the pulse peak, you can also have the intensity of 10 to the 17 about 1 picosecond earlier, 10 to the 15 around 2-3 picosecond earlier, 10 to the 13 watt per centimeter square around 4 to 5 picosecond earlier. So is this intensity can these intensities also ionize the target? And if yes, can we see a pre-plasma evolution of that? That's the main question. So laser pre-pulses, as we showed, causes a pre-plasma, and this pre-plasma can completely vary can change the main can change the interaction with the plasma. So there is a need of measuring this pre-plasma evolution or the pre-plasma scale length. But as I told you, as the main pulse has not still appeared, this pre-plasma scale length can be very, very small. It can be very extremely small as compared to lambda, can be of the order of nanometric scales. It actually hugs the surface before even the main pulse's arrival. And we need to measure this pre-plasma condition as and how they occur. This pre-plasma is basically very important to measure because this can actually decide the laser absorption of the main pulse. This can help, this can decide how energetic can your electrons be and how they are getting transported. High pre-plasma can affect your high harmonic generation. You need cleaner and cleaner pulses to get more and more high harmonics. And also mostly the simulation guys which use this pulse as an ideal pulse need some basis where they can use this data for their computer simulations. Yes.
Calculate 10 power 17 watt to 90 watt to 76 square. You actually divide the entire intensity that you measure, the energy that you measure in the pulse. So I have to first integrate that entire curve, then divide by the femtosecond time scale, and then that's how I get it.
Yes.
But when you start giving this number as a function of time of this entire rate, where are you integrating? Which part are you integrating?
Okay, basically, as you are saying, we are integrating only this part, but also this has enough number of photons which can actually ionize.
When you say that intensity,
Yes.
Intensity, see, when I say 10 power 19 watt per centimeter square,
Yes.
it also has a femtosecond
Correct.
division. That's
Correct.
Goes 90 watt.
Correct.
Now, when I'm say 10 picosecond before,
Yeah.
the intensity or 5 picosecond before, the intensity which I'm calculating, which you are saying is of the order of 10 power 13 watt per centimeter square. What is underneath what is the time scale that we are considering, or what is the energy that we are considering?
Okay.
But this number should come not from just the graph, but from the actual meat of the pulse is there, and you have a tail, and it's how bright the tail is, how long the tail is.
Yes.
So how this tailing is done? Because it's not just the clock, it's something more than that, right?
Yes. So what we are trying to say is, suppose I have 2 joule of an energy and I consider it to be 25 femtosecond only, then I can reach very similar to 10 to the 19 watt per centimeter square. But suppose I have this laser pedestal where there can be a certain amount of energy already exists. And from that, suppose you try to calculate, you may get a very low intensities. But what we are right now here talking about is only the peak intensity and not the intensity which is scaled because of this free plasma. So what we basically talk right now is a peak intensity. There, of course, there is an intensity which is much lower than that and coming ahead of the several times. But we are considering only the femtosecond part when we talk about this 10 to the 19 watt per centimeter square.
I think his point is that intensity has delta T,
Yes.
and you cannot have something like instantaneous intensity.
Yeah.
So that is the thing.
Yeah.
But if
Exactly.
it scales it like this.
Exactly.
I mean, with some scaling, and this is one, this is a million
Yeah.
times lower, like. But strictly speaking, that's, I think you're right.
Yeah. But what we are talking, as we are saying, it's only the peak intensity right now. And so what are the ways to measure this pre-plasma scale length? So there are several techniques. One of the technique can be a shadowgraphy technique. But the shadowgraphy is not can help you to find where the critical surface is. You can see the channels created by the hot electrons, but you cannot actually point out the pre-plasma generation here because of the target has a very certain age which creates a diffraction, and this diffraction is of the order of the incident wavelength. Can you use Doppler spectrometry? Doppler spectrometry in principle is highly sensitive. Ultrafast technique, as I have showed you, but that technique is not very sensitive to the pre-plasma because it has to reflect from a critical surface which has to be dense. So under dense, it's not very helpful to measure, and you cannot see the shifts because of the shifts due to the Doppler spectroscopy, and you cannot find out a laser pre-plasma. You can, of course, use interferometry. A special interferometry also you cannot use because it's limited to lambda by 2 to lambda by 2, lambda by 4 resolution. But what you can use is a frequency domain interferometry. The advantage of this is very highly sensitive for a direct phase measurement. And this phase can give you the resolution of the order of nanometrics scale. The basic requirement here is you need to interfere 2 identical femtosecond pulses in frequency domain. So first, how to create 2 identical pulses, and second, how to interfere in them time that we will look into. To create 2 identical collinear pulses, what is the simplest way is to use a Michelson interferometer. So we have used we have taken the probe to this Michelson. We have built a Michelson interferometer. There is a delay stage. With the help of this delay stage, you can basically you can basically give the time gap between 2 collinear pulses. So time delay can be managed with the help of delay line, and overall this can be with the help of the retro moved, where you can have the interaction before and after or within the pulse. How to interfere once you create these 2 pulses, how to interfere then in a frequency domain. So you take them to the spectrometer. Spectrometer basically do the linear dispersion, and basically this grating makes the pulse width longer and longer, and then you can nicely over them, you can beat them in the frequency, and you can see a nice fringes in frequency. So this is how you can interfere these 2 pulses. But even though you create such a nice fringes, the basic problem with this interferometry is the vibration. So it's extremely sensitive to ground vibration. As you can see, our breadboard is attached to this chamber. The vibration are also coming because of the vacuum pumps which are running all the time, and also acoustic vibrations can lead to move this Michelson mirror slightly, and what you get is not stable pulse to pulse not stable pulse to pulse fringes. So there is always a small jitter, and if you are such kind of a jitter, you cannot actually find out the phase, because phase requires completely non-jittery inputs. So how to provide the active vibration isolation, and how to basically make them stable pulse to pulse. So Ankit and Mr. Sunil Shetty from TIFR Auto Workshop worked during a COVID time. They have visited several labs, AFM, TM, STM. We actually do this on day-to-day basis. They have tested several prototypes. They have tested air tubes, several spring systems, and they have come to some solution. They have isolated this breadboard from the experimental chamber. They have put some adhesive and isolator at the legs. They have also used a different combination of springs and two breadboards here. So this above breadboard is isolated from this breadboard, so it's floating basically, and all the natural vibration happening from the pump running, walking, acoustic vibration is completely taken care by the spring mass system. And before, you used to see such kind of jumps, but after this vibration isolation, what you can see is a very nice stable fringes, and now they can be totally used for the FDI measurement. So this is basically a pump probe configuration which we are talking about. These two identical ultra short pulses, what we one call as a reference, another one as a probe. So first gets reflected from to the target and goes to the spectrometer. Then the pump pulse come. So we can run it again. This get reflected. Probe, pump pulse come in between them, creates a plasma, and now probe gets reflected from this created plasma. So what you can have is the fringes without pump, and then the phase shifted. The fringe shift because there is a plasma present there. So any phase shift due to this change, any fringe shift due to happening here is because of the phase shift happening into the probe pulses. And you can actually time this very well, and you can get the information of the plasma. Even before you can get the information of pre-plasma also. So this is the complete experimental setup. The main pulse basically gets split into two again. One part is used as a probe pulses, another one is pump, focused onto the target here of the intensity of 2 × 18 watt per centimeter square. This small part of the probe is converted into second harmonics, fed to a Michelson interferometer, and then you create two identical pulses and you focus specially matched onto the target here. And by varying the probe, so probe timing, you can decide whether you want to study the plasma related phase shift, or you want to study the pre-plasma phase shift. It's under your own control. So this is how the spectral interferogram will look like. Every time I'm comparing this red, which is without the pump, with the plasma or pre-pulse related spectrogram. This is at -5 picosecond. You can see a very, very small phase shift. When pump and probe of match together, you can see a huge shifts. And when it's completely dominated by plasma, you can actually see large amounts of fringe shifts. So fringe shifted interferogram you can back calculate the phase and you can infer the scale lengths from here. So there is a numerical recipe by which you can actually retrieve the phase. And this is how the retrieval phase look like. So you can have the shift in radian, which is of the order of 0 to 2 or maximum 3 till time t is equal to 0. And when there is a high density plasma, the huge change in the phase can be seen. From this, we have back calculated the plasma scale lengths. And now you can see that the free plasma scale length can as low as 3 nanometer at -6 picosecond. Yes.
How do you measure the density of the patient? Understand you get some different densities for different patients, but how do you measure the density of temperature of the patient?
Density from the
From the patient, you can measure the properties of the plasma.
yes.
How do you measure that? I understand you get the patient.
Yes.
How do you measure the properties? How population you do?
Okay, from the phase shift, we can clearly calculate the pre-plasma scale lengths because from the phase shift, from the retrieval algorithm, already the phase as well as the scale length parameter is being incorporated. From that, basically, you can calculate the pre-plasma scale lengths. For the intensity, by looking at, the temporal plot, you can estimate what kind of intensities are responsible for creating this amount of scale length, which I will show you in the next slide. So that way we can actually, the numerical recipe, we will help you to estimate the phase as well as it will help you to estimate, yes, and the scale lengths, yes.
So see, I understand from this first plot that you are getting this for different frequencies, you are getting different phases because there is a refractive index which is changing.
Yes.
But at the same time, the scale length, the length of the plasma is also changing. So you have now two parameters.
Yes.
One is the refractive index and the other is the length.
Yes.
You have to play with both. How
Yes.
do you pinpoint that it is because of refractive index or because of the length? Because we are converting that into this plasma scale. But do you consider in that time the refractive index has not changed?
Okay, what exactly? So during at least a pre-plasma condition, we are saying that it's a very low density underdense plasma. So we are here saying that refractive index is not playing a major role. But as time progresses, which we can say from 0 to 10 picosecond, where the refractive, though it's a very hot dense plasma, the refractive index is definitely quite different here. So, but to see to monitor the pre-plasma scale length, we are not considering the refractive index to be, we consider it to be very minimal and not affecting the pre-plasma measurement.
Yeah, because the refractive index will also have a spatial distribution.
Yes.
Right? That we don't know.
Yes.
But what we see is an integrated effect of the length,
Correct.
spatial distribution,
Correct.
even the temporal distribution.
Exactly. Exactly.
Some time to pass. So you have to consider something.
It is an integrated
Yeah.
effect.
Yes. Yes. It is integrated effect. We initially consider it to be very minimal at pre-plasma scale length, but of course it's quite high at hot dense plasma.
For how much of ionization. I mean, if you use this on Doppler shift will give you only the velocity. The phase shift can also be because of the velocity. So what Ankit and I think he's trying to figure out is that how much is because of Doppler and how much is because of the motion and how much is because of the ionization. The refractive index changes because of that as well. The cooling.
And another question is, you are not showing the curve, that is lower plot, but you have a lot of scatter around it.
Yes.
Are there some active oscillations there, or is it just a general scatter? Because your error bar is fairly small.
Yes.
Compared to that scatter. So is it because it can be genuine oscillations around?
Yeah, it can be. Right now, I don't have answer for that, but it can have genuine oscillations. We may have to do more measurements actually to find out whether these oscillations are genuine. But as you can see that the error bars are low, there can be an oscillation. There can be the oscillation which are like, which may be related to something like a terahertz oscillations, but we haven't checked it.
The error bar comes from the number of times you have.
Number of times the averaging we have done.
It's a standard error, it's not standard deviation.
No, yeah, exactly.
So what is the averaging? You should probably say how many shots were taken at each.
So I think for each of the data point here, we have to take 5 to 10 shots, and they have been averaged, and that's how we also get an error bar regarding that. So 5 to 10 shots per delay has been taken to measure this one data point.
Because you are measuring just the phase,
Yes,
you are just measuring the shift.
yes,
You are, changing.
yes.
So one is definitely your stability of your spectrometer, how accurate you are measuring and what is the jitter. What else is a contributor to this? Because suppose if I do one shot instead of 5 shots, what will be my error bar?
Yeah, exactly. So your error bar can be huge. So that's why, because the pre-plasma condition depends upon basically the energy you putting it onto the target. So even that may fluctuate point to point. So laser energy will fluctuate, laser pulse width will fluctuate. So overall, there are several parameters which are fluctuating. So that's why we are actually also the target conditions from one location to other location may have different chemical composition. So there is a combined effect of all this. But for a time being, we have taken a 10-point shot average.
Because when you arrive at that error bar, it is not just the standard deviation of 5 shots, right?
True.
It's something more than that. It also encompass all these systematic errors which are coming from different position, energy fluctuation, and also your spectrometer resolution.
Yes.
Ankit, you could add something?
Yeah, as you already said, I don't want to go to stability of the vibrations, stability of the electron, that is the body can calculate. And with the numerical, I don't know.
Numerical error, because of the algorithm.
Yeah, and then show to those stability how, because of the one different plasma condition, how it works. So all the error will be taken upon and then
It's not easy, yeah.
But then why don't you error bar for all the data points look at the same size?
Yeah, no idea. But they are there. This is 10-point averaging, and
this was not the final. This was the very first data. We improved this data with the next minute.
okay. So we may have for the a new set of data where you may see the
error bar two is that's what I told you. So it's the stability of the overall vibration and show the plasma condition how they do. That's how the variation is.
Yeah, that's okay. But it is the standard deviation, but different part, the error bar could ideally be generally different for different spots. It seems like they are the same for others.
Yeah, it could be different, but yeah, we have the 14 different.
These error bars, so the other conditions that we talked about are contributing to this error. The bar bar incorporates those errors also. How do you account for the error?
Yeah.
You know,
So different plasma conditions will be the different ratios. That's
No.
correct, but there has to be a scale.
See, for example,
scaling is very difficult.
I'm measuring current, okay, and my least count of the current is 1 p.m. Then, and if I know that my current measurement is fluctuating in the last digit, then I know my error is 1 p.m. Then whatever I calculate, I use delta I and 1 p.m.
Yeah, so that one we go, that second digit, that you are saying is likely in our case is very because of the vibration. So because of the plasma condition, whatever is happening, that may take a successful thing over here. Because we take multiple shoots and then see what.
It's not easy to disentangle all the.
I agree with that, but that's what I'm asking. That's why I'm intrigued with the estimation of the error.
It's not about the error, the fact that this is of the order. For example, 3 nanometer may not be 3 nanometers, it's of the order of nanometers. And the errors are, so this is actually the first measurement done. If you ask me, nobody else has done this. All the people, I think the reason they don't do it is that probably it's not an easy experiment to do, number one. And number two, most of these people are just obsessed about some other signal coming, ions and electrons and all that. They assume something in the simulation and put it there. We are now trying to tell them that this is the simulation scale that you should be taking. Pre-plasma was always taken as adjustable parameter
Yes.
to interpret the results. Like get what you want by adjusting the pre-plasma. So now we will tell them you can't do that because of this order. So order magnitude is established, but the exact details I think are very difficult to unravel.
Okay.
Okay. So, yeah, I will quickly go to my last topic. And as we have talked more and more now about the real high intensity laser, which looks like this. So can we actually clean this part? So there are several techniques where will be standardly using a second harmonic technique. It is the best way to improve a temporal contrast because intensity of second harmonic goes as an I square. As I earlier showed you that we have 2 omega already generated as a probe, but onto a very small crystal, and conversion efficiencies are also very small, as you were pointing out. To really create such pulses and use them as a pump pulses, you also have to consider that our real laser spot of real laser beam size is of the 80 nanometers. So you need a big crystal, big SSG crystal. So you have limited options. You have BBO, KDP, LBO. Most of these crystals are hygroscopic, and that's why they have very shelf life. So you have to completely passivate their surface to use them in a correct way. You have to consider the phase matching conditions in vacuum, and this crystal should also help and should sustain the large fluence which we will be putting onto. And yeah, they may not be available. We have done a long search for several years, and we found out this company who basically got ready to develop such grow such crystal for us. So they give us a crystal which is an LBO of 70 mm diameter, and they have tested it with something like 25 joule per centimeter square damage threshold. We asked them to specifically coat them with a protective coating on both the sides, both the surfaces, and also the anti-reflection coating for both the surfaces. And the phase matching conditions provided by them were not very difficult and can be managed inside a vacuum. But what they couldn't guarantee us is a conversion efficiency. So we, of course, have to, once we got this crystal, we of course have to measure the conversion efficiency. And this is how we set up for this. So Aparaj basically led this effort. We have used our main laser pulse, put an LBO here, input energy of the pulses being measured by this one of the OFIR detector, OFIR energy sensor. We have used 2 dielectric mirrors of 400 nanometers, so 99% gets reflected. 0.1% of 800 may also go here, but most of the 800 being transmitted back and put onto the beam dump. The second actually further purifies it. We also use a BG930 to further purify this, and now we can also put one more energy meter here to find out the conversion efficiency. So with the help of this 2 energy meter input and output, we can basically find out the conversion efficiency. So this is how we have done it inside a experimental chamber. This is an LBO mounted into a very solid mount. It can have the theta as well as phi rotation to match the phase match, to have a good correct phase matching condition, correct K vector condition controlled outside the vacuum. And then we fed it into 2 different energy detectors. And this is what we have found. So with increasing input energy on the LBO of 800 nanometer, we could see that it's also going nicely up. And this is the efficiency curve. Efficiency curve basically gets flattened out around something like 70%. But this is great, meaning we could achieve a 70% of an conversion efficiency from this crystal. And this actually has opened a new era in the lab, that now we can use this ultra intense 400 nanometer pulses. The contrast of these pulses cannot be measured by third order autocorrelated because that limits to 10 to the minus 12. But if you see a theoretical curve, it can actually, suppose my pedestal here is 10 to the power minus 9 for 800 nanometer, it can actually have 10 to the 18, or at the worst case, it can have 10 to the 13, 10 to the 14 to be very safe. So what we have created is extremely clean pulses and extremely intense pulses to find out some number. Now we can routinely generate in lab 500 to 700 millijoule of this SSG pulses of the diameter of 7 centimeter. We have also developed a frequency resolved optical gating technique to measure the pulse width. We have found something around 60 to 70 femtosecond pulse width of this 400 nanometer pulses. And we can nicely focus on to the, say, 7 to 10 micron focal spot. We can reach the intensities of the order of 10 to the 19. And now if you see this plot here, so suppose now this is 10 to the 19, 1 picosecond ahead, you will have 10 to the 12. So ionization threshold is actually being completely washed out. You can see that this is beyond ionization threshold, and that means we can clearly clean these pulses and can be used to measure basically a laser matter interaction. This is how it looks. It looks beautiful when we are taking out one pulse out for the measurement. It completely floods the lab with a blue color. And this has opened a new venture, new avenues for all of our students. And this can be the real future of a field lab very soon. Aparajit has basically developed a self-diffraction frequency resolved optical gating to measure such pulses. He's also interested in absorption of such ultra-intense, ultra-contrast laser pulses. Ankit is working on measuring 2D Doppler velocimetry and also 2D frequency domain interferometry. And Deepak and Niladri will measure protons, ions, neutral atoms at the target front and target rear. Anandam will do the self-generated magnetic field measurements using such ultra-clean pulses. And we may be moving to the next step, which is we may start measuring the high harmonic generation from such an ultra-clean pulses, and Sagar and Rakib will lead this effort. So I'm thankful to all my group, which we know as an Afil family. Not only group, my own family, my colleagues and their family. So thank you all of them. These are some past students and well established in their field, and they have also a collaborator in several of these experiments. We have nice collaborators from not only from TIFR, but also from all over the world. And I like to extend my acknowledgement to the central workshop. They have worked enormously for several of our tools development. They are working non-stop most of the time for some of the things needs to be developed here. And as I told you, we have upgraded this laser from 100 terawatt to 150 terawatt in 2019. We required a huge support from TIFR electrical section and TIFR central services. This is a new chiller which we have installed, and we really had got a good support from electrical and central services. So I acknowledge them in this from this ground. And to summarize, we have developed a 2D velocity map, developed the technique, and now can nicely measure 2D velocities. We have developed a plasma nanoscopy, pre-plasma scale lens can now be clearly measured. We have generated ultra-clean, ultra-intense SSG pulses, and future will be this, and can be the topic for next ASSET colloquium. And with this, thank you very much.
Okay, so thank you, Amit, once again for that really uphill task of covering such a large space of science and also, of course, the technologies which has led to kind of very impressive results. And also, I think several questions that have brought up during your talk that actually made more insights into the work that you've been kind of doing. And also, thank you for deciding your next asset colloquium. So, yes, I'll do. So, are there any questions by the time? Professor Datar, you can go ahead. You can unmute and ask your question.
Okay, can you hear me?
Yes.
Yes.
Okay. I have actually a couple of questions. First question is there a possibility of going to, let's say, about 200 nanometers as well? Doubling the doubled frequency, which you have very nicely achieved.
Okay, so I haven't covered this part here. What we have routinely generating in lab is 266 nanometer, which is a third harmonic of these pulses. And we are using them for measuring basically for pump probe dynamics. We haven't gone to 200 nanometer yet, but as I'm talking that we are interested in high harmonic generation from this plasma, we may in future use this 200 nanometer, which is just a second harmonic of the 400 nanometer pump pulses, which we are going to generate. But in near future, of course, yes, 200 nanometer will be used, generated and routinely used in our measurement.
Okay. Can I ask a second question too?
Yeah, please go ahead.
Okay. What limits the power density? I mean, the power per unit volume. Is it that the bandwidth of this laser pulse itself, or is it some other, fluctuations in the spatial extent of this focused laser beam?
So the intensity.
What
limits the
intensity?
So basically intensity, as we are saying, we have 27 femtosecond laser. We can go up to 5 into 10 to the 19 watt per centimeter square, but it's actually depend upon how sharply you can focus these pulses onto the target.
Yeah, that's right.
How
What
we
is the
could,
limitation?
So that was his point, I guess.
yeah. Till now,
Just one second. Professor Datar, you have something else to ask?
No. Just
Or rather clarify?
No. I just wanted to know what limits the actual focus, the size of this
That's
focus.
yes,
Is
actually,
it the optics or is it something else?
yeah, basically you can go close to diffraction limit or thrice the diffraction limit, and that's the diffraction limit basically limits your focused intensities onto the target. If we can do a nice spatial phase correction and use the nice way to focus to operate the off-axis parabola into the vacuum, we can really reach up to the 2 to 3 microns of the focal spot. But as we are saying, the diffraction limits the focal spot width. Yes.
Okay, thank you.
Flat top form of your pulse itself will limit your focus. Because that diffraction limit is your original pulse being Gaussian.
Yes.
Your original pulse is not Gaussian, you will have additional constraints on.
Actually, nobody really knows the shape. We assume that it is whatever we like.
Yeah.
But these multiple amplifiers on the way.
Yeah.
And every amplifier adds its own.
Correct.
setup.
And whenever you do the focal spot measurement, you have to do it extremely low. Extremely low.
That's
Yeah.
been a big surprise. We
Yes.
also have this adaptive optics mirror now, which adjusts the phase.
Yeah. So the
And,
spatial phase.
So with the adaptive optics, pretty much like what astronomers use, it's been taken from astrophysics to astronomy to laser focusing now. So we have a mirror which tries to correct the distorted wavefront to a plane wavefront and then try and focus it, but up to a certain level. Not like, and of course we can shrink the pulse duration and say somebody says go to 5 femtoseconds, but 5 femtoseconds will need a bandwidth which is hundreds of nanometers. It's about 192 nanometers at 800 nanometers. Where do you have an amplifier for that? And where do you have any optics for that? So these are dreams, but or you can go to attoseconds if you like.
Okay.
To boost up.
Any questions? Any more? Any more questions? Yeah.
I have a stupid technical question. Due
Nothing
to
is stupid.
vibration, how much error you can have in time delay between pump and probe pulse?
Okay, so our probe pulse width, which I was showing, is something around 80 femtosecond. So that's where it limits you. So up to 80 femtosecond, you can have a nice pump probe delay. So it's only limited by the
No, due to vibrations, your distance may get changed.
that's actually very minor, and we are actually checking before each and every interaction. The measurements are being carried out. So I don't think that limits it, but only the pulse width is what limits it. And if the pulse width of 180 femtosecond can, if you convert it into the space, it will be like few tenths of micron, around 30, 40, 50 microns. So that actually much less than the vibration which you have on the target. So it's limited by the pulse width.
Yeah, I think I don't see any more questions. So once again, let us thank Amit for his very nice colloquium. I must apologize. Normally we give a memento to the
No.
speakers. Right now it is under production. You will get. Sorry about that. Really. Okay, so let us join for a cup of tea in the West Canteen. Thanks.
Okay, thank you.
Yeah.
Amit, very nice talk.